morning, everyone. Thank you for attending this presentation today. I'm Dong-Weon from Jeonnam National University. Today, I will present a self-assembled smart scaffold for endovascular disease diagnosis. The order of the presentation is as follows. Nowadays, due to irregular eating habits, alcohol and tobacco consumption, the mortality rate from cardiovascular disease such as myocardial infarction is continuously increasing. With the exception of surgery, treatment options include inserting a stent and taking a thrombolytic agent. However, the vascular wall narrows again due to the narrowing tumor development within 3 to 6 months of stenting. In order to improving the narrowing of the blood vessel wall again, platelet inhibitors or thrombolytic drugs need to taken. But continuous drug administration cannot prevent hemostasis and surgical operation is required. Balloon dilatation and stenting are used to treat vascular disease. Balloon dilatation was first proposed as a treatment for 1980s and was proposed as a method of improving blood flow by dilating narrowed blood vessels without surgery. Stents were developed to prevent stenosis of blood vessel after balloon dilatation, and various stents were developed depending on the scope of the application, such as bare metal stent, drug-eluting stent, and bioabsorber vascular stent. According to the material and characteristic of the stent, it is divided into 4 generations. The first and second generation of the bare metal stents are made of stainless steel or quartz chrome and are the most widely used. However, it has side effects of third generation drug-eluting stent is a drug-released stent that inhibits cell proliferation and stenosis and is the most commonly used today. However, it causes thrombolysis. The fourth generation bioabsorber vascular stent is absorbed into the body when the blood vessel maintains its own diameter. A commercial product approval was revoked due to side effect. Stent insertion have the advantage of being able to operate in the simpler way than surgery and restoring blood flow, as shown in the following video. Bare metal stent, drug-eluting stent, bioabsorbable vascular stent, and recently sensor-integrated stent has been developed to treat blockage of blood vessel caused by plaque. A sensor-integrated stent was first proposed in 2006. A stent with an integrated sensor for insertion into the human body initially had the forminder, which the PCB and miniaturized battery are attached to the stent structure. However, this method causes a major eligible problem in the human body when the stent and the PCB are separated. In order to simplify the additional device, a sensor with a wireless transmission method was attached to the inside of the stent mesh. But there is still a problem with the adhesive strength. In order to improve adhesion and add various functions, a stent manufactured on a flat surface has been proposed. However, making a flat stent into a cylindrical shape still remains a problem. In addition, it is difficult to control the biodegradability of stents and sensors made using magnesium alloy. Focusing on blood pressure measurement, the proposed stent adheres the pressure sensor to the stent by micro-welding. However, additional wire are required for closed-loop configuration of the LC circuit. The fabrication of stent using a 3D printer has several advantages, but also suffer from limitation that crimping for insertion into the human body is impossible. To summarize the current state of art, stent undergo restenosis in which the lining of the blood vessel become narrow again due to the material and structure characteristic of the stent. Sensor integrated method in a stent having a 3D shape is not easy and affect blood flow. Periodic checkups are required after stenting, and time-consuming social problems remain due to cost and frequent visit. In our proposed self-assembled smart scaffold, the wireless pressure sensor integrated with self-assembled smart scaffold is expected to be used for patient-tailored medical service and diagnosis of various diseases by monitoring the pressure of the treatment area in real time and sharing the patient condition with the attending PTCN. A typical MEMS pressure sensor sensing method included capacitive and piezoresistive methods. Both methods are definable using simple formulas. In this study, a capacitive type pressure sensor was selected to achieve high sensitive and low power consumption using passive elements. The schematic shows the working principle of the proposed LC circuit. The inductor coil always has a constant value, and as a capacitor plate deformed according to pressure, the resonance frequency shifts. The self-assembled smart scaffold has the following shape in the plane, and is assembled in a cylindrical shape due to the geometrical difference between the residual stress and the structure after the sacrificial layer is removed. Before fabricating the overall sensor, each element technology was. This segment was formed through the copper electroplating process, and a flexible hinge was formed using SUA. The manufactured, the fabricated self-assembled smart scaffold structure can control the diameter by the length of the hinge. And as the length of the hinge increases, the diameter of the stent increases. The radial force of the fabricated structure was measured using a universal tensile tester, and the higher radial force can be confounded with an increase in the overlapping area in the stent with a small diameter. Next is the LC wireless pressure sensor. It is composed of the top and bottom plates, and adhesion and air cavity are formed using Perminex. Perminex is a negative tone photoresist like SU8. The biocompatibility of Perminex was confirmed through the cardiomide site culture. The fabricated top and bottom plates were attached using a summer press bonding method. The shape of the air cavity and the inductor of the bonded device was checked through the cross-section. The adhesive strength of the upper, top and bottom plates was checked through the tape peel-off test. Perminex offers two baking options. When the first soft bake was performed, the upper top and bottom plate were easily separated due to the adhesive strength of the tape. Second, it was confirmed that the little part of SU8 was separated only in the contact point area. In the sample that was completed until hard baking. To evaluate the characteristic of the fabricated sensor, a measurement platform was configured using vector network analyzer, syringe pump, laser vibromet, commercial pressure gauge, DA keyboard, LEPU-based GI, and vacuum chamber. In order to check the robustness of the fabricated pressure sensor, the pressure was lowered to the millitole range in the vacuum chamber, and the retention of the thin film was checked. In vacuum, the thin film of the pressure sensor was kept stable, and the resonance frequency was also kept constant. The displacement and the capacitance of the membrane with respect to pressure were measured. When a pressure of 140 millimeter mercury was applied, the thin film was deformed by about 10 micrometer, and the capacitance was changed by 0.125 picofarad. A self-assembled smart scaffold was designed by combining the basic process. After forming a sacrificial layer in a simple rigid segment was formed, and then a scaffold structure was formed using SUA. The inductor was formed using the metal electroplating process, and the LC closed loop was formed using a Perminex bonding process. And then the sacrificial layer was removed to self-assemble. The fabricated self-assembled smart scaffold is as shown in the top image. And the formation of the inductor and the contact point on the polymer structure was confirmed using an optical microscope. Through the initial resonance frequency measurement, it was confirmed that the self-assembled smart scaffold product set has a resonance frequency suitable for medical use. The characteristics of the wireless pressure sensor were confirmed in pressure environment and distance. It was experimentally confirmed that as the capacitor thin film was closer according to the pressure applied. And as the distance between the antenna and the sensor increased. To evaluate the characteristic of the sensor to be used in the in vivo environment, the resonance frequency was measured in the environment of air, DI water, saline solution, and culture media. Legion's frequency shift appear differently according to environmental change. However, if the environmental variable is removed, the Legion's frequency of the sensor return to its initial state. It can be said that the dielectric constant of the solution affected to the sensor. Finally, the heart rate measurement was confirmed using the biomimetic phantom system, and the Legion's frequency shift according to the heart rate change was confirmed. This result indicates the possibility of using the manufactured fabricated sensor as a blood pressure and heart rate monitoring platform. Conclusion. Optimization of unit processes such as bonding and rolling for the fabrication of self-assembled smart scaffold. Self-assembled smart scaffold production has been completed and characteristics are evaluated according to recognition, distance, and pressure. The SOA polymer-based wireless pressure sensor exhibits a Legion's frequency of about 54 to 426 megahertz, depending on the number of tons of the inductor. Cardiomyocytes were cultured to evaluate biocompatibility of the fabricated device, and the biocompatibility of the material used for fabrication was confirmed. A quantitative pressure application system has been established, and characteristics are expected to be evaluated according to the difference in pressure and dielectric. Future, we plan to conduct blood pressure analysis experiment using in the in vivo environment. Thank you. This work is supported by our leading research center and Sejong Science Fellowship of the National Research Foundation of Korea. Thank you.